Bismillahirrahmanirrahim. The, in the last phase of the previous lecture, we have explained this example. However, we can discuss on the previous lecture if you have any question. So I am looking for any question from the last lecture. Any question or comments, any discussion if needed. Okay. It seems that everything is fine. Okay, let's start today's session. So since we have already established that, you can remember this. This is xn is equals to a to the power n un. So what kind of series is this one? Definitely this is a right-sided sequence. Of course, you can plot it since a to the power n it is multiplied with un. So it is of course a right-sided sequence where it can be goes decaying or it can increase. It depends on the value of a. If a is less than 1, it will be decaying. If a is greater than 1, it will be increasing. And for both cases, both stable or unstable cases, we can solve this equation in the z domain. And we have found the result like this. We need two things. As I have already mentioned in the last class, we need to express it in the mathematical term, number one, as well as we need to represent the ROC by the graphical representation. What is the ROC of this section? Of course, we have found that the ROC will cover R, which is more than A. So the solution is more than A. All the values more than A is the solution plane for the Z domain representation. Okay, so that we have already understood from the previous lecture. We can follow some more examples and a few topics, and then we'll move to the filter design by the Z transform. Let's if we have our xn, which is equals to un r to the power n cos n omega 0, where you can find that the cos omega 0 n, which is a sinusoidal signal which has the frequency omega 0, a particular frequency, that is multiplied with r to the power n. Again, the question is, what would be the value of r? Okay, it can be any value. It can be more than 1 or less than 1, and then it is multiplied with un. So then again, this is a right-sided sequence. Okay, for this kind of problem, whenever you have the cos omega 0 n or sine omega 0 n, we can move to the Euler's equation that will help us to solve this kind of problem. So what we can do here, of course, un can be neglected in a way that whenever we'll go for the summation in the z plane, we'll write in a way n is equals to from 0 to infinity. That is enough, because for the value of n minus 1 to minus infinity, there is no value. So it becomes 0. So this part, we can consider only this part, because this part actually shows that this is a right-sided sequence. And for that right-sided sequences, we have already solved a problem, which is a to the power n un, and we know that solution from there. Okay, now if we go for the solution, we have r to the power n, and as we know that from the Euler's equation, cos omega 0 n is equals to e to the power j omega 0 n divided by 2 plus e to the power minus j omega 0 n divided by 2. So this is the expression by using the Euler's equation. So we can divide this equation in two parts, and now you can go for the Z transform. So you can do the Z transform of this section, and you can do the Z transform of this section. So we'll show that in future lectures. but you can do yourself and you can find the Z transform expression like this. And from this expression, this is the expression, and you need also what is the ROC of this this segment. So that means for this equation, and you can show that the ROC should be more than R for the both cases. As we have understood that when we have the right-sided sequence like a to the power n un, right-sided sequences, always the value of R, or you can say the amplitude of Z transform value, it is always greater than the Z value is greater than this value. That means it is, if we have some kind of circle, what is the circle value? Let's say the circle value is A. The solution plane is always outside the unit circle. That we have found from the previous example. So we can just remember this, but with a practical example, we'll show that definitely. So for a right-sided sequences, we can show that whatever the value here, or if you have a circle like this, the solution is outside of that circle. On the other hand, in a very short time, we will show that if that is a left-sided sequences, in that case, you will find, if that is the left-sided sequences, you will find that the solution plane is inside of that particular circle. So we'll show that example. So please do it yourself and solve it. You can also solve it for the sine omega 0 n, r to the power n, and un. You can take any value of those and you can get the solution like this. No need to memorize this equation, because if I want to have this equation, okay, first of all, you may need to solve this equation where xn is given and you need to solve it. Okay, that is another thing, but you never need to memorize this part, because if you need this, then I will give this data to your question paper. So no need to memorize this sort of equation. Okay. Another thing, so we need to explain more on that with the example. Before going to that, there is a practical aspect of the Z transform by which we can understand the zero and the pole location, or zero and pole interaction for a particular discrete time system. Again, we'll discuss it in the later part. However, we can discuss it here as well. So if we have yn in the time domain, if we do the Z transform, we'll get the Z transform value in the Z domain. Okay. So for any sort of Z transform value, we can represent any discrete system can be represented with the pole, the function of numerators and the denominators, with two functions of which have already Z transform. For example, if we think on in this way, if we have yn, this is a simple example, yn is equals to, let's say, yn minus 1 plus xn plus xn minus 1. If we go for the Z transform, what will be that? This is yz is equals to z to the power minus 1 yz plus xz plus z to the power minus 1 xz. So this is very simple. From this equation, if we want to write it here, we can take common of yz. If we take it in the left side, then we can find, okay, let's say 1 minus z to the power minus 1. And in the right side, if we took xz common, then we got 1 plus z to the power minus 1. Now we can write it very easily that yz divided by xz is equals to 1 plus z to the power minus 1 divided by 1 plus z to the power minus 1. Sorry, that will be minus z to the power minus 1. And this part, if you concentrate that this yz divided by xz, that can be written as hz, that means the response of the system. Output divided by input. So you can compare with this. So if hz, you can think about hz is gz, and pz is your yz, and qz is your xz. So any sort of discrete system, what is yz? Here is yz, hz is equals to yz divided by xz. So any sort of discrete system, this is an example of an arbitrary discrete system. Sometimes you may have that this part is equals to 0. If that part is 0, of course, this portion have been nullified in that case. So there is no pole in that case. If there is no portion of here, that means x n minus 0. If it is not there, then of course this part will be nullified, and you don't have any zeros in the equation. So I believe you understand the things. Any sort of, in general, discrete system, any discrete system can be converted as a rational function of pz and qz, like this. If that is so, then we can expand that equation as I have shown in the earlier equation, like 1 plus z to the power minus 1 divided 1 minus z to the power minus 1, where what is the coefficient here? The coefficient was 1. What is the coefficient there? The coefficient was 1. There can be any sort of coefficient. So if we can write in this way, we can also do it like that. So p1 z to the power minus 1, where p1 is the coefficient, and 1 plus there is a q1, that is another coefficient. So I should put minus here for the previous example. So we can put the coefficient. So how many coefficient you have? So it depends on what is the how many x delayed values are there. X n minus 2. It depends on how many values are there. So it depends on the delayed input sample. How many of those you have found. Similar to that, this denominator shows how many delayed values of the output. N minus 1. Y n minus 2, you have 2 delayed values. So if you have higher values of delayed function in the discrete domain, you have higher coefficient values are there. So what is the coefficient here? Let's say the coefficient is q1. Here is the coefficient is q2, something like that. Okay. So we can write it like this. Very good. Afterwards, you can just go through this mathematical terms. It's not very difficult to understand. We can put it like a, this is of course a polynomial. This is as a polynomial. So we have two polynomials, the ratio of between two polynomials. Now we can express it as the root value. We can express it with the multiplying factors, where we can find the roots. This symbol is that it is the multiplication. So this gives the summation, and this represents the multiplication. So how many multiplication terms are there? It is from L to M, because we have M factors, M delayed input values. Similarly, we have L to N. Why is that? And because we have N numbers of delayed output sequences we need to represent this equation. And from there we can do the calculation. You can just go through this, and afterwards you can find this sort of expression, which is the same as the previous one, by which we can find how many zeros are there, and in the denominators we can find how many poles are there. Of course, by these, if for example M shows the number of zeros and N shows the number of poles. By the equation, you can find it. However, we have another part is here, that is Z to the power N minus M. How we got that? For example, if we have, let's say, N is equals to 4 and M is equals to 3. That means we have four poles and 3 zeros. Put it in the equation. Okay, we have found this. Afterwards, whenever we are considering this term, that will show Z to the power N minus M. What is that? That is 1, Z to the power 1. So that is in the numerator. That shows that it also gives a 0. What is the location of the 0? The location of the 0 is equals to add 0. Because as you know that how we can find the 0 location. Z minus epsilon L is equals to 0. From there, we can find what is the 0 location. What is the 0 location? Similarly, if we have a Z to the power 1, that means Z is equals to 0. What is the 0 location? That 0 location is at the 0. If we have N is equals to 4 and M is equals to, let's say, M is equals to 2. In that case, we got in this term as Z to the power 2. That means Z square. So that means Z square is equals to 0. In that case, we can find that there are 2 zeros at the 0 location. At the 0 location means at the center. At the center, we have 2 zeros. There is 1 0. There is another 0. So we have represented by the number. So if you have overlapping zeros at any location or overlapping poles at any location, if you have 8 poles in the same location, we can write it like this. Let's say this is the Z plane. You have 8 poles in some locations. So you need to write, okay, the 8 is there just to represent how many poles are there. So on the other hand, if you have, let's say, N is equals to 2 and M is equals to 4, that means you have 2 poles and 4 zeros. In that case, what will happen? You can find that Z to the power 2 minus 4, that is equals to Z to the power minus 2. It means that this is 1 divided by Z square. So now this is in the denominators. So how many poles are at the 0 locations now? How many poles are there? Extra 2 poles are there. Extra 2 poles are there. So previously you have 2 poles. By this equation, what is the number? From this number, you found that what is the pole number, and you got extra 2 poles here. Previously, you have 2 poles and you are getting extra 2 poles. So how many poles are there? So altogether, you have 4 poles. How many zeros are there? You have altogether 4 zeros. So from this general equation, we can find that if you have 100 poles, there should be 100 zeros. So the pole number and the zero number should be always equal. Whether they are at the center or they are at the infinity, doesn't matter, but they will contain the same number for any particular cases. Okay. Okay, this shows, this actually gives the extra poles and the zero numbers at the center location. Okay. Of course, we have particular examples, so don't be panic with the mathematical terms. Definitely, we'll give some example in very short time. This is another example. Let's talk about a very practical example in our engineering problem. Let's say our sequence is like this. This is a finite sequence. This is a zeroth sample. This is n equals to 1, and this is n equals to minus 1. Now we need to find the xz and also the ROC of the sequences. Okay, in general, the equation we have wrote in this way: n is equals to from minus infinity to plus infinity. Do we need to write it minus infinity to plus infinity? No, because as we know that our sequence is from -1 to +1. So this is from -1 to +1. And then we have xn and e to the power, no, e to the power, this is z to the power minus n. That is the expression. Now, for minus n is equals to -1, we should write x -1 and z to the power minus 1. So that is +1. Plus, of course, plus, because this is summation, x n equals to 0 and z to the power -0, that is 0, plus x1 n equals to 1 and z to the power -1. And you can put those values over there. So the coefficients can be put in the subsequent portion. So x -1 is equals to 1. So we can write z to the power -1 plus 2 z to the power 0 is equals to 1 plus z to the power -1. So this is the expression for hz. This is the mathematical expression, and we have found this. Good. So I made a mistake here. Yes, this will be z to the power 1, not -1. Z to the power 1. Okay. Now we need to write the equation. We can write the equation in this way: z plus 2 plus 1 divided by z. That can be also fine. Now, can you find the ROC of this equation? What is ROC? You understand that for which value of R you have the solution. That is the ROC. What is the range of the value of R? Let's start with 0. Can we take the value of R, or you can say z modulus is equals to 0? If we can we get the value for, we got the solution for hz. If I put z equals to 0 there, what will be there? It will give infinite, isn't it? It will give infinite. So infinite means that is not soluble. So it is not given any number. If the z is bit higher than 0, are you getting the solution? The answer is yes. Yes, we got the solution. That is the starting point. So what is the starting point? More than 0. Exactly 0 is not our solution. So I can write it here: hz is equals to z plus 2 plus 1 divided by z. If for any value more than 0, we got the solution. Okay. Other extreme point is infinite. If we take z is equals to infinite, can we got the solution here? The answer is no, because in that case, this is an infinity, plus 2 plus 1 by infinity. That of course give an infinite value. So what is the ROC? We can say that the ROC is starting from more than 0 and up to infinity. More than 0 and up to infinity. How to express it in the 2D diagram in the z plane? If you have the z plane like this, we can put a circle, a dot over this. This dot shows that it is not included and the whole z plane. What is the difference between whole z plane and apart from the 0? Here the ROC represent that the z should be more than 0 and the z value should be less than infinity. That is the ROC. You can write the ROC as the z or R, whatever the case. It should be greater than 0 and less than infinity. And in the 2D plane, you should put a dot over there. If the ROC is like this, let's say the ROC is like we have Z, and that is less than only infinity, and 0 is also a solution. In that case, the plane would be like this, the whole Z plane. There is no dot at the center. Okay, so that is the difference, but you need to understand what we are telling here. So the ROC, you can write here R is greater than 0 and less than infinity. That is the ROC, and we got the expression as Z plus 2 plus 1 divided by Z. That is the value. So this is for a finite two-sided sequence. Okay. For the right-sided sequences, which is a causal, we already know about the causal signal. If that is a right-sided sequence, that is the causal signal. We have A, B, C. If that is like this, it can be expressed like this. Can you find the ROC of that? It's very simple. Again, put the value for different value of Z and try to find the value, find the location, find the domain of the ROC. First, let's start with 0. Is 0 is a solution? The answer is no. 1 divided by Z will give infinite. So 0 is not a solution. So we need more than that. What about infinity? What about infinity? For this one, if we put infinity, yes, infinity is also a solution. Infinity is also a solution. So the ROC is more than 0 and up to infinity. More than 0 and up to infinity is the ROC for right-sided sequences. So how we can put the show the ROC? The whole spectrum. Rather, just put a dot, because 0 is not a solution. And what about the infinity? Can you show the infinity? No, it's not possible. So in a language or in a sentence, you can write it. The ROC is up to infinity, more than 0 and up to infinity. That is the ROC of the right-sided sequence. From this equation, you can find it very easily. For this expression, this is a finite series. And in the previous example as well, this is a finite sequence. So we are talking about finite sequence. Anti-causal sequence, that is a left-sided sequence. As you can find that we have Z and Z power, positive power. So you can take 0 is also a solution. But what about infinity? Infinity is not the solution. So the ROC, 0 is a solution. 0 is a solution. So no need to put any dot in the center. It's up to infinity. But infinity is not the solution for the left-sided or anti-causal signal. Yes, 132.
Sir, in the previous example where infinity was part of the solution, in that case, in the diagram, will we shade the diagram or will keep it empty?
The last part of that of the 2D plane you are talking
Yes,
about.
Yes,
there is basically, whenever we are plotting it, definitely you have some square box. Sometimes we thought in a way there is a square box. So where is that infinity? You don't have the limit. So that's why you can just put it up to the end part. That shows that, okay, it's up to infinity. Whether infinity includes it or not, you need to write it in sentence. That is how we are actually expressing the ROC.
Okay, sir. So in that case, we can write Z is less than or equal to infinity, or
Exactly.
we can write it
Exactly. For this kind of expression, the 0 is not the solution. So that's why we are putting a dot like this. I'll show the plot in just a minute. And we need to extend it up to infinity. If you are putting a box, that will help us to understand, okay, you are throwing your lines up to infinity or not. But if infinity also a solution, and if infinity is not your solution, there is no way to express it in the graphical manner. So that's why you need to write it in sentence. Okay. Okay, thank you. So this is for the anti-causal sequence. I believe that you understand the basic things. Again, this is if this is a two-sided sequences. We have shown the example previously, and we have found that the ROC is more than 0 and less than infinity is the ROC for this kind of two-sided and finite sequence. We have already shown that for infinite sequence, the ROC looks circular. We have done it for we have done it for UN. What is the ROC? We have found the ROC. You can we have done this example. We have found this. This is the mathematical expression. From this, we can extend it to this z divided by z minus 1, where it shows we have a 0 at z equals to 0, and it shows that we have a pole at z is equals to 1. We have pole and the 0, and we can plot it like this. So what is the distance of this circle? The distance of the circle, this is 1. This is 1. And what is the ROC? We have already shown it in that example, previous example. The ROC, that means z, should be greater than 1. So what is the, how we can put the ROC? This is more than 1. And what is the final destination of that? Up to infinity. So more than 1, it shows that it is up to infinity always. So you can write it like this. It actually shows that, okay, it is up to the infinity. But by the graphical representation, you can't show where is the infinity. Okay, that's it. We can understand this. Always this circle, the circular representation, it actually starts from a pole, not with a 0. This value, that means the restriction of the ROC or the bindings of the ROC always start with the location of the pole if you have a single pole. If you have multiple pole, definitely we'll talk about this with an example. But what is our main motivation of this example? For infinite sequences, the ROC are in circular pattern. In case of finite series, what we have given the example before, 1, 2, 1, where 2 is in the center. In that case, this is always the whole plane with or without 0 or with or without infinity. So that is the concept of the finite series, finite sequences. However, when it is a infinite sequences, in that case, we have already shown that the ROC looks like a circular pattern. So there will be some ring or circular expression you will find in the Z plane. So we have shown this example. And similar to that, we have done this example just in the last class. And we can show that this is the expression. And from there, we can write like this, where we again find that z equals to 0 is the 0 location, and z equals to a is the pole location. And from that 0 and pole location, you can draw it. This is the 0 location, and this is the pole location. Let's say this is the pole location. What is the distance? The distance is a. And what is the ROC? The ROC is z should be greater than a. So more than a, all value is the ROC. So if we need to draw a circle. Circle looks very odd. Still, I can't draw the circle properly. Okay, so more than this. Of course, this looks like a circular format of the distribution. This is again for the infinite series. For the finite series, you have the whole plane with or without the 0 or infinity value. Okay, here we are presenting one example where we have two sequences. Let's say we have two sequences. Of course, we can express it in a single expression or the equation, but if you can think properly, we can have two parts here. 0.2 to the power n un plus minus 0.6 whole to the power n un. So you have two signals, and you are actually joining those two signals together. So if we want to do the Fourier transform, definitely this is the expression where it is under this format, a to the power n un. So you have done this before. So that's why straightforward we can write it like this: 1 divided by 1 minus a z to the power minus 1. So here a is 0.2. So we are writing that. Similar to that, the second portion, there will be plus, and the second portion 1 divided by 1 minus a is here minus 0.6 and z to the power minus 1. So pretty simple. From the hn we can find the hz. Now there are certain things we can find. What is the ROC of this one? This is straightforward. Since we have, okay, since the value of a is 0.2, more than 0.2 is the solution. Of course, that's why more than 0.2. Here we have a minus 0.6. Still, you can understand that whether this is a minus or plus, it doesn't matter with us. Let's say if we have a to the power n, definitely it will multiply with r to the power minus n. So it will give a to the power n divided by r to the power n. So we need to choose the value of r in such a way that it will counterbalance the value of a. From that expression or from that logic, we can find that this a divided by r whole to the power n, that should be this part should be less than 1. That part should be less than 1. If that is so, we can find that the value z value should be more than 0.6, since a is equals to 0.6. So whether this is a negative or positive, of course you understand the point. If I can elaborate the things again, 0.6 whole to the power n un. If that is your sequence, this is only the sequence, then what would be the z value? Let's xz is equals to summation for n equals to 0 to infinity, because we have un. So that's why I'm writing 0 to infinity minus 0.6 whole to the power n z to the power minus n. Z to the power minus n means r to the power minus n and e to the power minus j omega n. So we are considering, of course, in the last class we have found that we are considering that this part should be less than 1 for the summability. So we can write it as I have already mentioned here. We can write minus 0.6 whole to the power n divided by r to the power n, and that should be less than 1. Which one should be less than 1? Minus 0.6 divided by r whole to the power n. So this part should be less than 1. If we start with that, minus 0.6 divided by r, that should be less than 1. Okay, and in that way we can find, if we put r should be greater than 0.6 minus. Okay. if we change the example in a way that if this is a plus, the r should be more than, in that case r should be more than 0.6. What does it mean? When we are plotting the z domain representation, whether this is the point for 0.6 minus, or this is the point for 0.6 plus. Of course, that is a circle, and more than that is the solution. It actually contains whether this is a negative minus 0.6 or positive minus 6. They are actually make the same things, because this r value should be greater than, with a number 0.6, the modulus of that. So modulus value of that, which shows that the modulus of z should be greater than 0.6. Whether this is a positive or negative, that doesn't matter, because we need more than 0.6. So here we have found that this is the ROC and this is the ROC from this expression. And okay, so I have just shown how to do the calculations of this one. Okay, so I have expressed here with the same thing. If this value should be less than 1, so from there we can find what how we can show that the z should be greater than 0.6. So r should be greater than 0.6, even if there is a negative number. So from this expression, if we extend the equation, and we can write this expression as a pole zero format, so that we can find the pole locations and the zero locations. From this equation number 1, we can find this is the 0 at 0 and 0 at minus 0.2. Similarly, we can also find that the pole at 0.2 and pole at 0.6. This is just the pole and the zero location, and we can plot it in our z-plane. So try to consider here the poles and the zero location. So 0 at 0, here is that. 0 at minus 0.2, so this is that one, the second one. And the pole at 0.2, this is the, and the pole at minus 0.6, so 0.6. Of course, this signal is a infinite series, as we have that. So for the first signal, that means 0.2 to the power n un, we have found that the ROC is greater than 0.2. So that means we can put a circle. Okay, we can make a circle like this, and more than that. So we can draw it here. Don't forget that this is minus 0.6. For the second equation, the second part, we have minus 0.6 whole to the power n un. For this one, what is the ROC? The ROC, z should be more than 0.6. So we can draw the ROC. Let's say this is the circle of the radius 0.6 and more than that. That is our solution. So now, what is the combined solution of xz, or we have given as hz? What is the combined solution? The combined ROC is this one. If we draw that, the more than 0.6 actually includes both the ROC. From 0.6 to 0.2, there is a solution for this part, but we don't have the solution for the second part. Where we have the combined solution is the solution for this Hz. So for Hz, what is the ROC? For Hz, the ROC is G is greater than 0.6. That is the value from 0.6 to infinity. So whenever you have a complex signal, in a sense, you are adding two signals together. In that case, we need to think that where we have the common solution, and the common solutions actually give your particular ultimate ROC of that signal. Okay. So you can draw the ROC. We have already drawn the ROC of that signal. Okay. There is an exceptional example here. We can put, let's say xn is equals to a to the power n. We don't have un there. We don't have. So that means it is a two-sided sequence. For any value of n, you got the sample. So if I draw it like this, we have the value here. In the both side, we have the value, and this is an infinite series. If it depends on the value of a, whether a is more than 1 or less than 1. It depends on that, whether it will decreasing or it will increasing with time. Okay, but this is a both-sided sequences, but this is an infinite sequence. Yes, 132.
Sir, in the second sum term, will it not be from n equal to minus infinity? Oh, okay, it's -1 because 0 is already included.
Yeah, you are talking about this example?
Yes, sir.
Okay.
The second summation term.
Yeah. So I'll explain the things, inshallah. Okay. So we are dividing, just for understanding, we are dividing this whole section in left-sided and right-sided sequences. For left-sided sequences, we are taking n is equals to from 0 to infinity, and plus for the right-sided sequences, the n is from -1 to minus infinity, or you can say from minus infinity to -1. So those are the two sequences we can divide it. Now we can concentrate on the right-sided sequences. From our experience, we have already shown that the a to the power n should be less than 1. So we can find the z value. The z value should be greater than the amplitude of a, or you don't need to even put the modulus in the left side. Okay, so you don't need to put the modulus in the right side. which belongs to the r should be greater than the value of a, and this is from our previous example. If we twisted the things, of course we can show it that in the second case the r should be less than a value, plus or minus, so less than a value. How we can show that? If we replace the sequences of n with a negative value, we can write it very easily that it is like from n is equals to 1 to infinity, putting n is multiplying with a negative value. In that case, a is a -1 and z to the power n. So whatever the things you can find the amplitude, in that case it is z to the power n divided by a to the power n, and where this value should be less than 1. From that concept, you can, if that is less than 1, of course z should be also less than a value. So for the left-sided right-sided sequences we got this, and for the left-sided sequences we got this. So now if you draw the z plane, and what is the value of a? Let's say the value of a is 0.5. A is equals to 0.5. So I draw a circle over there where this amplitude is 0.5. So for the right-sided sequences, the solution is more than 0.5. More than 0.5. That is the solution. And for the left-sided sequence, the solution is less than 0.5. So what is the solution? This is the solution. So do you have any common solution there? The answer is no. And since there is no common solution in the z-plane, you don't have any solution for xz. Since there is no common solution, you must have a common solution to have the z transform. However, we can find that, so it concludes that we do not have any z transform for xn is equals to a to the power n. However, we know that by the Fourier transform we can do that. So this is an exception where we have the Fourier transform, but we don't have the z transform. That is a specific example on that note. Okay. Please, I'll show this table within a minute. Examples from the Procreus book. Please go through this. Those are simple but important examples. Please look at that. This is table number 3.1. This is from the Procreus book. Let me enlarge a little bit. Okay, so in the left side, it's shown the signal, and in the right side, it shows the ROC. So as you have asked about how to show that, so this is the way how we can express the thing. And in the third column, it shows the expression how you can write in a sentence or more than one sentence. So if that is a causal and right-sided, definitely causal means right-sided sequence. So I'm talking about the first example. And as we have found that this is a finite, this is a finite, not infinite. If that is an infinite, so there should be some dot. So for the finite sequences, causal sequences, as we have already mentioned that the zero is not a solution. So how we can write entire z-plane except z is equals to 0. That is good enough. And how we can put it? There is a dot and the whole plane. That is fine. If that is anti-causal, it is, we have already shown that anti-causal and finite duration signal. Anti-causal, finite duration, we can also find that the entire z-plane except z is equals to infinity. So entire z-plane, the z is less than infinity. That is the thing, but you can also express like this. And in that case, 0 is also a solution. That's why there is no dot. So you do not need to put any dot over there. Two-sided sequence, of course, whenever we are marching these two, the two limitations will be there. So the entire z-plane except z is equals to 0 and z is equals to infinity. Those are not the solution, and that's why we are putting a dot there. So if you can see, this one and this one looks exactly the same, but you need to differentiate between the expression written here. Okay, and for the causal signal, infinite duration signal. Now this is infinite. Infinite duration signal, we have found that there will be a circular format, and more than that is our solution. Don't need to memorize the things. By the concept, you should understand why there is a more than or less than, because from the expression you can find a to the power n, r to the power minus n. For infinite positive series, definitely that is a divided by r, and this portion should be less than 1. So from there we can put r is greater than a. Whether this is a positive or negative, it doesn't matter. Whether this is a positive or negative doesn't matter. How we have already proven it with example. For example, if I put a is equals to 2, I have shown that if a is equals to 2, so 2 to the power n, it will give 1, then 2, then 4, 8, something like that, it will goes bigger. Similarly, if I put a is equals to -2, so whole to the power n, whole to the power n, I have shown in the last class, it will goes like this and this. So that is the expression. So at the first value, it will start with 1, then negative value, then positive value, then negative value, and positive value. In the both cases, whether you are taking a is equals to +2 or -2, the r should be, in this case, the r should be more than 2, and in this case r should be more than -0.2. More than 2, sorry, not -0.2, more than 2, not -0.2. So in the both cases, r should be more than 2, just to suppress the concept. Because if I put 2 divided by 2, more than 2, that is 2.5, definitely that will down sample the value. So the modulus, this 1, whenever we are talking about 1, we are neglecting this plus or minus value, because we are talking about this modulus value, the summation. If we have a -5, let's say, whole to the power n, that is not summable. If you have a -2 whole to the power n, that is not summable. Again, if we have 5 whole to the power n, that is not summable, and +2 to the power n, that is not summable. In the both cases, if we have 5 plus or minus, the r should be more than 5, and that will be justified, whether this is a negative or positive. Okay, for anti-causal, remember, this is infinite series. In that case, the solution should be inside of that. So we have already shown it by the example. What was the notion of that? Since for the anti-causal, it starts from n is equals to -infinity to -1, a to the power n and z to the power -n, and we can write it, if we flip it through, that n is equals to -n. That will flip the things. So in that case, n should be start from 1 to infinite, and a to the power -n and z to the power n. And with the same logic, we can write z should be less than any value. So let's say less than a, or with this example, this is R1. So that will give the interior of that solution. If that is a two-sided sequence, we'll show that with another example. If that is a two-sided sequences, it's very interesting. Let's say R1 more than R1 and R2. This R2 is for right-sided sequences, and this R1 is for left-sided sequences. I'll give more example on that, but at this moment we can show it very quickly. So I have drawn two circles, one circle and two circles, where the first circle represent the R1. The first circle represent R2. R2. Yes, this is R2, and the second circle represents. Let me choose another color. This is represents R1. So R2 comes from the right-sided sequence. So what is the solution for the right-sided sequence? What is the solution plane? Of course, the exterior. So you have the solution exterior of that. And for R1, since this is a left-sided sequence, the interior of that. So interior of this. This is interior. And where is the common solution? If I took another color, where is the common solution? The common solution is inside R1 and outside R2. That is in the annular format. So that is the ROC. The Z should be less than R1 and Z should be more than R2. Sometimes it may happen that if this R1 R1 is less than R2, in that case, you don't got any solution. For example, if this is R2 and this is R1. We have R2, this is R2, and the solution is more than this. And where is R1? Let's say this is R1. R1. What is the solution? Inside of that. Do you have any common solution? No, you don't have any common solution. In that case, you don't have any Z transform of that sequence as well. Okay, I believe that this is enough for today. So if you have any question at this moment on today's lecture.
Sir,
Yes.
the ROC is kind of an indication of how unstable the system is. Is that right?
Yeah, of course. This is a very good question. That if we have, let's say, we have talked about the unit circle. Think about this. Let's say this is the unit circle, where its distance is 1. Let's say for a causal system, causal infinite series, for example, this infinite series, if we got, let's say, alpha, how we can write this equation? Alpha to the power n un. And if the alpha value is 0.5, in that case, where is the pole? Of course, you have the idea now, by now, that the pole is at 0.5. You'll find the pole at 0.5. So if you find the pole at 0.5, you have the circle like this. And what is the solution? The solution is exterior. By this, you can find that, of course, the unit circle also inside your solution. That means your system is stable, because the Fourier analysis, you can only do the Fourier analysis for the stable signal. For the unstable signal, you can't do the Fourier analysis. So since your solution plane includes the unit circle, it shows that your system is stable. And now if you increase the value of alpha to 0.9, definitely it will be very close to unit circle. It will very close to unit circle. And that shows that you are very close to the instability. But it's a very simple format in a way. First value is 0.5 and second value is like 0.9. By observing the pole in the Z plane, you can understand how much the system is stable and unstable. Of course, the pole location and the ROC are the same for the infinite series. Now, if alpha is equals to 1.3, where is the pole? Of course, there, 1.3. By observing the Z plane representation, you can understand that, of course, the system is unstable. You don't have any solution in the Fourier domain. However, you can put a comment on the instability, whether the system is very unstable or a little bit unstable, with considering that if you have alpha is equals to 2, definitely this gives a more unstable situation. I'm talking about a very simple system. When it is a very complex one, then you can even understand more about the system, system representation and the instability of the system. Now the question is, even if the system is unstable, let's say you have, I'm talking about the real pole, not the complex pole. If the system is unstable, how to make it stable? Okay, you can change the pole locations, or you can put a 0 in such a way so that you can counterbalance that instability of the system. I believe you got your answer.
Yes, sir. So for the example, the exception example that we had, it had no ROC, but it has Fourier transform. So
Exactly.
the system is stable. It's just an exception that we don't have ROC for this example.
Yes, that is true, that you don't have the Z transform represented, but you have the Fourier transform. And whenever you have the Fourier transform, as we can represent it in a way that, of course, for the right-sided, and for the left-sided, the sequence should be okay. If I go to the example, try to look at this, the two-sided sequences. For this kind of two-sided sequences, it should be like this. However, if the sequence is like that, increasing in one side or something like this, and decreasing other side, or increasing one side and decreasing other side, in the both cases that is unstable in a way that if that is increasing in any side, that actually gives unstable situation, isn't it? So there is a consideration that even if this is a stable situation, but we need to consider that in the for a two-sided sequences, that should goes like a stability for both cases. But for any other cases, even that is unstable, you can do the Fourier transform. That is an exceptional case. Even this is a unstable situation, it makes an unstable situation, because for any value of A, at least one side of the sequences, whether right side or left side, that that shows instability, even though you have the Fourier transform. So that is a exceptional thing. Okay.
Okay, sir. So this system is unstable then.
Of course,
although it has Fourier transform, but
exactly,
no ROC.
Exactly.
Thank you, sir.
Okay, welcome. Okay, thank you very much for your participation.